Okay, so here's another example using nodal analysis. So this is a more complicated circuit, obviously. This has, we're going to find that this has 3 nodes. So let's just get started going through the procedure. First thing we want to do is identify the reference node. So we still want to put the reference node on the bottom in this case. So we want to put it on the bottom because the bottom has the most connections to it. Right, so we talked about that in the previous video. Now we want to identify any nodes that we already know the voltage at. So here's one of those, and here's another. So at this point over here on the left, we have, positive 12. And here on the right, we have, okay, so this is tricky on the right. So it's a source labeled with this polarity, and the voltage value is negative. So whenever the number is negative, that means you have to flip the polarity and make it positive. So this source would be the same. Hold on. This source would be the same as that arrangement right there. Okay. So we've labeled all of the known nodes. So actually we didn't write that in here. So the voltage at this point would be plus 9 volts, right, based on what we just did right here. Okay, so now let's go through and label all of the unknown nodes. So I see one right here. There's another one right here. And one more right here. So those are the 3 nodes I can see. Do we have any others? For example, this is my ground. My ground goes all the way up to that point. I don't see any other nodes. So these are going to be the 3 node voltages we want to find. So let's call that VA, VB, and VC. Okay. Now we have to write KCL equations for these nodes. So remember, nodal analysis involves writing KCL equations for the nodes and then converting those KCL equations into voltage divided by resistance. So let's start with VA and let's find all of the currents. Right, so remember, I like to assume all of the currents are leaving the node. So let's see how many currents there are leaving that node. So we have one going that way, going up, one going down, another one going down, one going to the right, and one going up through R1. Maybe I should be a little more clear. There. Okay, so there's 5 currents there we have to write in the KCL equation. And remember, the way I'm doing it here, I'm assuming none of the currents are going in, so they're all going out. So let's just start writing the equations. So for the current going downwards, we have VA on one side of it. On the other side, we have positive 12 volts. So VA minus 12 over 680. So that's one of the currents. And then the current going up, so this current, that is VA minus VB over 220 plus, let's say, this current going down, that one's going to be VA minus 0 over 1.2K. And then this current going through R8, that one is actually VA minus VC, right? Because VC extends all the way down to that point. So that's VA minus VC. Divided by 1K. Alright, and there's one more. This current going up right here. That one is VA minus VB over 390. And all of that has to equal 0. So when I simplify this, so that's all the VA terms. So 1, 2, 3, 4, 5 of them. 1, 2, 3, 4, 5. And let's look at the VB terms. So we have, what do we have? We have minus VB over 220 and minus VB over 390. So I've written out all the terms. This is going to be my equation 1. Now I just need to get numerical values for. Okay, so now I've gone ahead and simplified all that. Got numbers to represent all of those coefficients. And now we can move on to the second equation. Alright, so I have the circuit cleaned up now. I'm going to start doing the second node, VB. So VB is going to have 3 currents, one going to the left, one going down, and one going to the right. So starting with the one going to the left, goes the one going down. Oops. So on the other side of R1 we have the voltage VA. Then finally the one going to the right. Okay, so that's the second equation. Let me double check that. So the VA term should be negative, the next VA term should be negative. Both of the VB terms should be positive. Actually, there should be 3 VB terms. I made a mistake. And for VC, it should be negative. Yeah, so that looks good. Okay, let's get numerical values for these. Okay, so I came back with those numerical values, and this is going to be our simplified equation 2. Alright, now we can... Alright, now let's try to solve the third node, VC. Let's write all the current equations for this node. So this is actually going to be pretty ugly. It's going to have a current going to the left, to the right. It's going to have this current I1 coming in. If we want, we can also write that as negative I1 going out. And then going downwards we have another current, and one more, and one more. So 1, 2, 3, 4, 5, 6. 6 currents. Alright. I'm just going to leave it flowing in for my analysis. I'm not going to change the direction of that current. So let's go ahead and start writing all the equations. So the top left current, that's going to be VC minus VB over 220. The current going to the right, the left, downwards. Now this all has to equal 50 microamps because this is the current in, and the left side of the equation is the current out. So it's current out equals current in. Okay, let's do some simplifications. Okay, so then we also have one more term. That's this term over here. So that term is negative 9 over 1.5k. So I'll just move that over to the right hand side. And then it'll become positive. Okay. So that's my equation 3. Now let me get numerical values for this. Okay, so here are the numerical values. Alright, that's my final equation 3 there. Alright, now I have solved the system of equations, and these are the values that I have obtained. 5.79, 5.34, and finally 4.649. Alright, can we do a check to see if this is any good? How about we go to PSpice? Okay, so PSpice agrees with us for VA, right? Because it's got this listed as 5.795 volts. And then how about VB? VB should be up here. So that's listed as 5.351. So that's really close. And then VC is listed as 4.656, and we got 4.649. Alright, so that looks good. Just like a slight rounding error probably because I put in some rounded numbers into my equations. So we can use PSpice to check our work on these nodal analysis problems, which is pretty convenient.